So it's my great pleasure today to introduce to you Professor Jonathan Lin. And Jonathan's recently a professor, and he just joined this last fall in the Earth and Atmospheric Science Department. So we all know, I think, that this tremendous destructiveness of tropical hurricanes and tropical storms. In the last year, they killed maybe 300 people in the US, caused over $100 billion in damages. And so the impact of climate change on these systems and their frequency and intensity is a really important problem. And luckily, that's what Jonathan is studying. So Professor Lin attended Princeton as an undergraduate. Then he went on to MIT to work with Kerry Emanuel. And then he took a postdoc at Lamont Doherty, affiliated with Columbia, before he came here about 6 months ago. So in general, Jonathan's interested in how the tropical atmosphere works and how this impacts hurricanes and tropical storms. And he's also interested in the impact of these systems on people and how it'll impact us in the future, how it impacts people now. So thank you very much for coming.
Great, thanks, Peter. It's great to be here. Thanks for having me here. And today I'll talk about the physics and risks of hurricanes in a changing climate. And hopefully you'll get something out of this. And I want to emphasize that what we do is a lot of physics, but we also want to use the physics to do actionable science, which you'll see later. So how do I go? Okay, so today we'll be talking about tropical cyclones. They're also known as hurricanes here and typhoons. The etymology of this word is a little bit interesting. Hurricanes can be derived from I think it's a Cuban god, Huracan. And these, of course, you might know, are massive swirling storms. This is a satellite picture of a tropical cyclone. And you have the winds that rotate in the northern hemisphere counterclockwise, so the winds are rotating like this. And they bring about a lot of destruction to places that they impact. And they really, as Peter said, they cause billions and billions of dollars of damage every year. And so it's important to be able to understand them, not just for the sake of understanding, but also to predict them. So I'll show a little bit of some pretty images for you. This is a animation of a tropical cyclone from space, and what I'm showing you is brightness temperature, and you don't actually need to know what brightness temperature is, but it's essentially the darker the colors, the more rain there is. So it's a measure of precipitation and clouds, and you can see it's a massive swirling storm. The winds are and this is in the northern hemisphere. This is a tropical cyclone that was near Hong Kong earlier this year, and there's lots of rain near the center of the storm, and you can see this clear patch over here. This is where the eye of the hurricane is. So this is where everybody knows the eye of the hurricane is typically clear and free of clouds. So you will have, if you ever pass through an eye, it's actually quite amazing to see. And in the outskirts, you also have what we call spiral rain bands. And there's a lot of features here that we could go on and study about. But this is one example of a hurricane from space. But it's important to remember that hurricanes, although maybe it's important for me, I study hurricanes and I often study them using models or theory, and we don't necessarily understand the impacts the impacts are not necessarily in our face every day. So I'm showing you these pictures to show what hurricanes do to society. So these are the next few slides I was showing are pictures from Hurricane Otis, which affected Mexico last year. And this was really a tremendous case because it was a tropical storm, so it was a very weak storm. And then literally overnight, it intensified to a Category 5 hurricane in the span of 24 hours. So in the morning, there was just a tropical storm warning, and then immediately the residents woke up to a Category 5 hurricane. And of course, associated with this was a massive loss of life, but also property. So here is an example of wind damage that was caused by Hurricane Otis. These were in the mountains. This is near Acapulco. So there's a mountainous range just inward of the coast. So these are mudslides that happened as a result of the rainfall from this hurricane. And this is some more flooding, collapsed highways. So these are really tremendous societal impacts that these hurricanes have. And even though for me, I study this, from afar, they do cause a lot of damage to society. So what about inside the hurricane? So this is a video from a sail drone. So these, you can deploy them in hurricanes. So this is a picture of, or a video of what's captured on board, the onboard camera from the sail drone in Hurricane Sam a few years ago. And you can really see intense winds. There's really a lot of rain. It doesn't really look like much is going on because it's all just sea spray. So it's very violent winds. It's very, very hard to survive this if you're ever in it. And of course, this is just what's happening in the hurricane, and this can cause a lot of storm surge, which is the flow of ocean water on shore. And finally, this is a satellite imagery of Hurricane Helene. So Helene was another storm that happened last year in it made landfall in the Gulf Coast of Florida, but then it was associated with around 4 feet of rainfall in some parts of North Carolina, and that was what we saw, a catastrophic flooding event there. But I wanted to point out one of the features of these hurricanes is this swirling around the center of the storm. Just go back here. And really from these satellite images, you can see lots of cool things going on that we won't get into today. And these are fascinating physics, but there are real world impacts from these hurricanes. So a lot of people ask me, well, what powers a hurricane? Everybody says, the ocean gets warmer, hurricanes are going to get stronger. And that is true in today's climate, but it's not necessarily true. And hopefully today what I want you to take away from this is a little bit of the nuances behind hurricane physics. So what I'm showing here is a fancy little parameter, which we call the equivalent potential temperature in the atmosphere. You don't need to know what it is. All it is a measure of how much energy there is in the atmosphere. What I'm showing is a cross-section. These are estimates from flying into a hurricane. This is Hurricane Inez in 1966. So on the y-axis here is pressure, and you can think of this as height. So the higher you go up, the higher in the atmosphere you're going. So planes, we like to fly around 300 hectopascal, for example. So that's much higher in the atmosphere. And then the x-axis here is the radial distance from the center of the storm. So this is the center of the storm, and then as you go to the right or left, you move outwards radially. And so what you can see here is that the brighter colors are showing you where there's more, that the equivalent potential temperature is higher, or there's more energy. And you can basically see that there's a lot of energy at the center of the storm. That's where the eye wall is. That's where the strongest winds typically occur in hurricanes. So there's essentially huge energy transfer from at the center of these storms, and this energy gets exhausted to the upper troposphere. So hurricanes draw energy from the ocean, and I'll talk a little bit more about the nuances behind what this energy is. But they draw energy from the ocean and export it to the upper atmosphere. And this energy transfer is what's driving the storm circulation and the storm strength. So you can think of this, I like this, the way of thinking about this. It's a giant wind machine that's sucking heat out of the warm tropical ocean surface, and then it takes that heat and exports it to the upper atmosphere. So what about this energy transfer? I was talking a little bit about it before. Energy transfer, there's multiple ways at which we can quantify energy. There's sensible heat, which we think about as thermal energy. So we all have sensible heat. Our bodies are a certain temperature. And we lose some of that heat to the environment. On a cold day, you lose some of your heat to the environment. And there's also latent heat, which is the evaporation. You can transfer latent heat through the evaporation of water. And this is how humans cool. We sweat, like I'm sweating right now, and we cool by that evaporation of the sweat to the environment. So that's a transfer of latent heat from our bodies to the environment. And so a similar thing can happen in the ocean, where you're transferring ocean water, evaporating ocean water into the atmosphere. And this is a crucial process, not only important for hurricane physics, but for the broader climate. So you can imagine this. I have a fan that's blowing. It's blowing wind. And I have an ocean surface. And what the fan is going to do, as it blows on the ocean surface, it's going to help or aid in the transfer of energy from the ocean surface into the atmosphere. And this can be in the form of sensible heat or latent heat, as I've just described. So there's a few points on this, and without trying to bore you with all of the equations, there's a few points at which we've learned over the course of many, many years. The first is the faster the wind, the more energy is transferred. And you all experience this on a really hot day. Or if you don't have air conditioning, you turn on the fan, and the fan circulates air, and it increases the rate at which energy is transferred from your body to the environment, so it cools down. This is all stuff that we experience on a day-to-day basis. And there's also a second point that's important, is the greater the difference, and I'll have here in quotes because we haven't really unpacked this yet, in the thermodynamic state between the ocean and the overlying air, the faster the energy is transferred. So if the ocean has a lot more energy than the atmosphere, then the efficiency of this transfer rate is going to be higher, faster. And as I said, if you experience this, it's harder to cool down in the summer than in the winter. In the summer, it's humid and it's hot outside, and so you overheat and you start sweating. It's your body's way of losing heat to the atmosphere. So in the summertime, the thermodynamic state of your body is closer to the atmosphere or the air outside than during the wintertime. Where in the wintertime, it's cold and dry, and so you will lose heat a lot faster. It's why we wear jackets, for example. And so all this physics you experience on a day-to-day basis. I'm just quantifying it here for you, and that it's the same thing that's going on for hurricanes. So tropical cyclones are fueled by this energy transfer from the ocean surface to the atmosphere. This is the key physics that's going on, and it's really, as I said, it's both the transfer of sensible heat and latent heat. And one can quantify the limit of tropical cyclone winds by modeling the tropical cyclone energy cycle as a Carnot heat engine. So it's a very idealized way of looking at this. Some of you might know what a Carnot heat engine is if you've taken thermodynamics or remember from AP chemistry, for example. But you can derive a theoretical scaling for how much energy can be extracted by using this idealized Carnot heat engine. And this is called the potential intensity, what we call the potential intensity. So it's kind of like a speed limit on the hurricane wind speed. So winds cannot go faster than this because that's the maximum wind that can be sustained by this Carnot heat engine. And so from now on, I'll be calling this potential intensity as this upper bound or this limit on the maximum possible tropical cyclone wind speed. So this is how fast your winds can get. It cannot get faster than this. And so this is the only equation I will show in this entire slide, so just have to bear with me. So what are the ingredients to the potential intensity? When you use an idealized Carnot cycle, you can write the square of the potential intensity as proportional to this first term, which is the temperature of the ocean, minus T cold I have here. I have the temperature cold as, it's basically the temperature of the upper atmosphere, and it's normalized by the temperature of the ocean. And then it's multiplied by this other term, which I call K ocean minus K atmosphere, which I haven't explained yet, but I will do so in just a second. So for those of you that might be familiar with Carnot efficiency, this is the Carnot efficiency of a hurricane. The Carnot efficiency is basically telling you how much heat you're putting in, how much you can convert into mechanical energy or wind. And so in this case, what this term represents is how much heat I'm extracting from the ocean. As I said before, the hurricane is extracting heat from the ocean, and it's converting that heat into kinetic energy or winds. That's how the winds are flowing It's creating kinetic energy from that. And so the Carnot efficiency in hurricanes is approximately 1/3. So about 1/3 of the energy it's extracting from the ocean gets converted into kinetic energy or wind. So that's the Carnot efficiency term, and I don't want to go more in depth into it than that. Okay, this last term is a little bit more complicated. This is the difference in the thermodynamic state between the ocean and the atmosphere. And so I could write this as K human minus K atmosphere, and that would represent the thermodynamic difference between your body and the outside air. But here I'm just saying it's the ocean minus the atmosphere. And in this talk, I'll call this the thermodynamic disequilibrium. It's a measure of the difference between the thermodynamic state of the ocean and the thermodynamic state of the atmosphere, a disequilibrium. And just like your bodies have a disequilibrium with the environmental air. And notice, if the atmospheric thermodynamic energy is higher than the ocean, then the potential intensity is 0. So you cannot transfer energy in the case where the atmospheric energy is higher than its environment. And you guys also experience this. If it's really hot or really humid, your body has no way of cooling down. That leads to heat-related deaths. So there's actually a theoretical limit at which this occurs, and this is it's called a wet bulb temperature, and if that goes above our body temperature, we cannot lose heat to environment, and human life will not exist. So there's a theoretical limit. Fortunately, we're pretty far away from it, but that's just another example of these kind of physics happening in the real world or the everyday part of life. And so the potential intensity depends on this thermodynamic disequilibrium between the ocean and the atmosphere, not just the temperature of the ocean. And this is a key point that I hope you'll take away from this. So what does the potential intensity look like? So I'm done boring you with equations. Here's what a map of the potential intensity looks like. So potential intensity, you can think of as it's this upper bound on what the storm intensity can be. And so here I have the potential intensity. It's in miles per hour. So a category 1 storm is probably around 64 miles per hour. And a category 5 storm is on the high end of this bar. It's around 155 miles per hour. So where the potential intensity is dark red, that's essentially saying that the atmospheric conditions here and the ocean conditions support a category 5 storm. It doesn't mean that there will always be a category 5 storm there. That's the wrong way to interpret it. It's just that this is the potential for a hurricane that occurs in this region. So you can see during September is the peak hurricane season in the Atlantic Ocean where we are. You can see the potential intensity is very high. Often, this is the average from 1979 to 2023. And the potential intensity can easily support a category 5 hurricane. This is what it looks like on September 30th of this year. This was a few days before Hurricane Milton. So for those of you that weren't following the news at that time, Hurricane Milton was one of the record-breaking storms in the Atlantic Ocean. And it had a peak intensity, I think, of 160 or 170 something miles per hour. So it was a very strong storm. And it formed in the Gulf of Mexico around here. And so you can see the potential intensity was also very high at this time in this area. Something other to note is that the potential intensity is high in the Western Pacific Basin, so over here near coastal Asia. And this is also a region where there's a lot of tropical cyclone activity. And somewhat in the Indian Ocean and somewhat in the Eastern Pacific Ocean. So these are the 4 hotspots for tropical cyclone activity in the Northern Hemisphere. And so if I flip back between these two, what I'm showing here is the climatology. So just all of the observations of hurricane tracks. So these are where the hurricanes have moved or where we observed hurricane paths over the past 40 years. And they're color-coded by the strength of the storm. So the brighter the color, the stronger the storm. And you can see, if I just flip back between these two, and sorry, it's not aligned completely, but in Asia, you have a lot of storms. Actually, it's the basin with the most number of storms. And it's also where we find the highest potential intensities. And likewise, we see storms, somewhat lesser in the amount of storms in the Indian Ocean and the Eastern Pacific, and the Atlantic also has hurricanes. Now, the Southern Hemisphere also has hurricanes, but their summer season is flipped from ours. So what I'm showing you here is September. I would need to show you this in February or January, and you would see the potential intensities being larger in the Southern Hemisphere. And so the Southern Hemisphere also has a lot of tropical cyclones. So essentially what you can get from this is that we have this theoretical potential intensity which we can calculate given a particular atmospheric and ocean state. And it can tell us where the tropical cyclone activity is. Essentially where this potential intensity is large, we have tropical cyclone activity. Of course, I'm oversimplifying this. There are other ingredients that are important for hurricane formation and intensification. Potential intensity is one of them and is one of the largest factors that influence hurricanes. And here's another figure that shows you the historical track density. So this is basically this plot, but now binned into histograms, so it's easier to see where there's a higher density. And you can see the West Pacific has a really high density of tropical cyclones. And this figure is a little bit misleading. The East Pacific has a high concentration, but it's a generally smaller basin, so it has less tropical storms than the Western Pacific does. And the Atlantic has a number of storms as well. And just the thing to remember is that the potential intensity is a really good predictor of where the hurricane activity is. So this class is about climate change. So what about climate change? We have this potential intensity. How does it change with climate change? This is actually how we started formulating our understanding of how hurricanes will respond to climate change. So before I get into what the potential intensity looks like in climate change, I first want to talk about how we first make predictions of tropical cyclones in general. So broadly speaking, we need to use climate models to predict the state of the atmosphere with continued greenhouse gas emissions and other things we're putting in, like aerosols. And climate models are really great for certain things. They're really great for telling you what the large-scale atmospheric state is going to be. However, tropical cyclones are really hard to model in these climate models for lots of different reasons. But one of the big ones is that because these models are really coarse. What they're doing is discretizing the whole Earth into different grid boxes and then solving equations, partial differential equations, to project that forward in time. And these models are too coarse to resolve tropical cyclones in general. So here's an example of a tropical cyclone structure. So here we have the famous or the well-known eye, and then the surrounding the eye is what we call the eye wall. That's where the strongest wind speeds occur. And of course, there's spiral rain bands and other things that happen in the environment. And the scale here, I want you to look at the scale here, is 50 kilometers. So an eye is typically around 50 kilometers from one end to the other end. It's very, very small, actually. And a climate model usually has a grid resolution of around 100 kilometers. So it just cannot resolve the fine detailed structure of a tropical cyclone. And this is a well-known problem. There are a lot of things that people are trying to do to remedy this issue, but this is one of the reasons why we have a difficult time understanding how tropical cyclones will change with climate change. However, this is where theory can be useful. And this is as I said before, this contributed to one of our first predictions of how tropical cyclones will change with increased CO2 emission. So recall our old friend, potential intensity. So what I'm showing you here is I'm calculating the potential intensity from a climate model simulation to 2100. So we take a climate model. This is a state-of-the-art climate model. And I'm calculating what the potential intensity trend is going to be in miles per hour per decade. And so where you see red is where the potential intensity is increasing over a 150-year period. And when you see blue, that's where the potential intensity is decreasing. So red essentially is saying that the thermodynamic energy available to the hurricane is increasing over time, and blue is where it's decreasing. And so one thing that I want to point out here is that it's red a lot in a lot of places, almost everywhere in the globe. Potential intensity is modeled to increase nearly everywhere with global warming. And this is really a result of the CO2 emissions And I won't get into the theory of this. You can also prove this theoretically. But this result has stood the test of time. It's not just this one climate model. It's all climate models. And so this intensity increase is really one of the driving factors between why we believe hurricanes will strengthen with climate change. And you understand now the basic physics behind why that's the case. The other thing I want to point out is it's not really even everywhere, right? Some places, the potential intensity is increasing a lot. I mean, it's off the color scale of this plot here. And in some areas, it's actually decreasing. So the potential intensity is not changing uniformly everywhere. And that's something actually that's an open question in our field. Why is it increasing some places more than others? It largely has to do with why the ocean temperature is warming in some places more than the others. But that's definitely an open question that maybe one of you guys will solve in the future. So why does potential intensity increase? We know this potential intensity is the speed limit on the hurricane intensity or wind speed. So recall our trusty theoretical equation where we have the potential intensity, or the square of the potential intensity being proportional to this Cornell efficiency times this difference in the thermodynamic state between the atmosphere and the ocean. So the Cornell efficiency actually does not change that much with climate change. It does change, obviously, because the temperature of the ocean is changing. But it's not the big factor for why potential intensity is changing. The reason why it's changing is because of this thermodynamic disequilibrium. The thermodynamic energy of the ocean is increasing faster than the thermodynamic energy of the overlying air. And that is why the potential intensity is increasing. So you can think of it as now it's more efficient for energy to transfer between the ocean and the atmosphere. So this is one of the key reasons behind why we believe potential intensity. And this does not happen in just one single climate model. It happens in all the models, happens in our more simplified models, and it also happens in idealized theory when you apply certain approximations to how the atmosphere changes. So this is a really robust result that you can go and tell your friends about. But this is just one equation. The potential intensity is this upper bound. It doesn't tell you how the average tropical cyclone will change. It doesn't tell you how the 75th percentile tropical cyclone will change. It doesn't even tell you how the tracks of the tropical cyclones will change. It's just a theoretical expression for what the upper bound of these hurricanes can be. We could imagine we live in a world where this bound goes up, but the fraction of storms that reach that peak intensity actually decreases. So then the average tropical cyclone actually decreases. So it's not a foolproof way of saying how hurricanes will change with climate change. And this is what our field has been trying to move towards more as actionable science, which is we do all this wonderful and beautiful physics, but how can we go and tell the average person this is what's going to happen to you in climate change? Or how, if I go to a city and say, do you need to build a seawall to protect yourself from a hurricane in the future? This is what it'll do. So those are the questions that we are grappling with right now, and I encourage a lot of you to think about this as you're entering the workforce or moving on in your academic careers. The primary way that we do this right now, there's many different ways, but this is one of the ways, is what we do is we call downscaling. So we take a climate model which cannot resolve a tropical cyclone. There are no tropical cyclones in it. And then we embed another model inside which is actually capable of representing tropical cyclones. And this uses physics mostly. And then we can actually simulate them given the atmospheric environment of the climate model. And this is going to be useful for evaluating tropical cyclone risk, which I will talk about more in this next section. So we're done with the physics part. Now we're going to move on to risk. So what is a downscaling method? So I'll go over it very briefly here. This downscaling method is pretty simple. All you do is you randomly seed tropical cyclone genesis points in space and time. So you're just seeding them randomly. You're just throwing a bunch of seeds everywhere. And then what you do is you evolve them in time. So we have physical equations that allow us to express how tropical cyclones will change in both space and time. And we just put that in and just say, okay, let this evolve in time. Let these random seeds evolve in time. And they are forced by the atmosphere that the climate model is simulating. So when you do this, what happens is most of the storms die out. Actually, most of the time, the atmosphere is not conducive to tropical cyclone formation. And we know this because there are not millions of tropical cyclones in the atmosphere at one time. There's usually around 3 across the globe at any time. So most of the time, the atmosphere is not conducive to tropical cyclone formation. But some of them do survive, and this represents some of the times when tropical cyclones are conducive or the atmosphere is conducive to tropical cyclone formation. This is kind of like a survival of the fittest process. You just throw a bunch out there and you see what survives. And then what survives, you can keep it, and you repeat this process many, many, many times, and you can get a large number of what we call synthetic storms. These are basically storms that we have modeled given a particular climate. They might not have happened in real life, but some of them do have analogs. So you can find a Hurricane Katrina-like storm in these synthetic storms if you have enough of them. So it's a completely open source model for those of you that are computationally adept. You can do it and run it yourself on your computer. But I don't suggest you do that right now. But you are more than welcome to do that. So how does this work? So I just have a few animations here. So this is the seeding process. This, you can imagine, we seed a storm right where this dot is. Then we evolve the track over time. So we say, according to the atmospheric environment, this is what the track of the storm looks like. And this is all going to be physically consistent with the environment that's simulated by the climate model. Then we can use the physical equations that was derived from theory, and we can say, this is what the intensity of the storm look like, or this is the strength of the storm along this track. So here I've color-coded the lines by intensity, so you can see this storm intensified prior to making landfall, and then it decayed, and then it strengthened before impacting southern Florida. And you can also fit a wind field to this. So these are parametric models that are describing how the wind changes over the course of the storm. And so this is just an animation of how we can simulate what the storm intensity or what the wind speed looks like across the storm. And so you can repeat this process many, 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 many times. You can generate millions of storms, synthetic storms, and use them to analyze what might happen in the future. And so as I just alluded to, we can generate a large number of synthetic storms, and I've actually done this, and you can force it, you can input a reconstruction of Earth's atmosphere over the past 40 years. So we have what we call reanalysis, or reconstructions, computer reconstructions of our best guess of what Earth's atmosphere looked like over the past 40 years. And these are largely based on observational data. So we have tons and tons of observations that we're making the model abide by, and then we're saying this is what the atmosphere might look like. And so we're using that atmospheric condition to drive this downscaling model. And it can be used to evaluate tropical cyclone risk. And this is the reason why this is important, is because to really evaluate risk, you need a large number of samples, right? If you want to evaluate the 1 in 1,000 year event, or let's say there's a 1 in 1,000 probability that if you walk outside, you'll slip on ice, right? You need 1,000 events to be able to simulate that. Now imagine if that 1 in 1,000 probability is 1 in 100,000. You need a lot of events, and we simply do not have that many events in the hurricane history. In the Atlantic Basin, we only have around 500 hurricanes over a 40-year period. It's really not that much to evaluate a risk. And here, when I say risk, this is defined by the IPCC as the potential for adverse consequences. So it's really a broad category, but tropical cyclone risk obviously are adverse consequences associated with tropical cyclones. Of course, as we said earlier, tropical cyclones cause billions in dollars of damage across the world, and in 2024 alone was estimated to $133 billion in losses. That's a lot of money. This is provided by a reinsurance firm. So there are really lots of societal ramifications from tropical cyclones, and we want to know, is it going to get worse with climate change? But the whole point of this, just to connect the dots, is that we have a model that can simulate a large number of storms, and you need to simulate a large number of storms in order to evaluate the risk. Now, the risk is important because it's one of the components that leads to damage costs. If the risk goes up and everything else stays the same, the societal costs will go up. And this is an equation that describes what the risk is. Risk is really a combination of the hazard. So here we talk about hazard as in the atmospheric hazard. So what is the wind speed? What is the rainfall rate? What is the storm surge? That's the hazard that the storm is associated with. It's multiplied by the exposure or the value of your particular property. So let's say you have a really expensive building, that's the exposure value. And then the vulnerability. What is the building code? If I have a poorly built building, it's going to be destroyed much easier than a well-built building. And this has largely to do with structural engineering and lots of things that are way outside of my expertise. So today I want to focus on the hazard, because this is the atmospheric hazard. And just so you know, you don't have to work on the atmosphere to work on this problem. You can work on exposure, you can work on vulnerability. There's a lot of engineering in here that's involved to make an impact on this. I'm talking about risk as a whole, but from here on I'll talk about hazard because this is what I do. So wind hazard can be estimated by using many, many synthetic storms, and all we're doing is evaluating the return period of a particular wind speed. So before I show you the figure, return period, some of you probably already know this, but it's just to measure how often would this particular wind speed threshold occur. So if the return period of, let's say, a Category 1 storm is 10 years, that's basically just saying every 10 years we expect a Category 1 storm to come by. So these are called return period curves. These are curves that you would very commonly see in cat risk modeling, so catastrophe risk modeling. So that's basically the modeling of catastrophe events like earthquakes or hurricanes or tornadoes. And how to read this is the x-axis is the return period and the y-axis is the wind speed threshold or the hazard. You can think of this as the hazard. So essentially for this model, at New Orleans, every 10 years we expect around a 60-knot hurricane. This is basically a Category 1 storm. Every 10 years we expect a Category 1 storm in New Orleans. And we can go further on. 135 knots is a Category 5 storm. New Orleans, according to this, has never had a Category 5 storm, obviously, because it's a pretty rare event. And this might happen every 1 in 150 years, so 3 times longer than our trustworthy record for tropical cyclones. So what this means is that you really have to use a model to be able to estimate what the tail hazard is, or the hazard is at high wind or at long return periods. And so the observations can tell us about return periods of storms with relatively low return periods in the 10 to 50 year range. But once we get out to the larger return periods, it becomes much harder. So you have to use a model in that case. Of course, you look at this plot and you'll say, wait, but nobody really cares about Category 1 storms. You know, you kind of just stay in place. Nobody's told to evacuate. And there is damage, but there's not a lot of damage associated with them. And so what you often have to do is multiply this hazard curve with a damage function. And this damage function is essentially telling you how much damage is there going to occur for this particular event. And so this essentially, the way to read this is fractional property value lost. It's just saying 10% of your property value is destroyed, or 50%, or 100%. And what I'm calling these damage functions are these functions that are just saying, okay, for this particular wind speed, this is the damage that a particular place would experience. And these are 2 different damage functions. These have to be calibrated to what we observe. So for instance, if we observed an event, 100-knot wind event that led to 25% property loss, then we'd have to calibrate this damage function curve. And there's a little bit of theory behind this, but that's kind of the, this is kind of the science behind how we relate hazard to damage at the moment. So we can use this model and predict the return period of a Category 1 hurricane. So what I'm showing you is the model on the top, the return period of a Category 1 hurricane, and what the observations look like on the bottom. The observation's a lot noisier than the model, because in the model we can generate lots and lots and lots of storms. But you can see that broadly speaking, the model can generally reproduce the observational distribution of hurricane hazard. So this is great to see that we have a model that can reasonably reproduce the real world. There are some obvious biases here, which you can point out, but it does a decent job of it. So now we have this tool that allows us to evaluate. We can put in a climate model state and evaluate what the tropical cyclone hazard will look like with climate change. So we can downscale climate models. So I was showing you on the previous slide, this one is downscaling our best guess reconstruction of the Earth's atmosphere over the past 40 years, but now we want to apply this to a climate model which is projecting the Earth's atmosphere in the future. So we can do this, we can downscale a climate model. I have an asterisk here because this is based on a single climate model. And this is what the return period of the 1 in 100 year storm during the pre-industrial conditions look like. And that's a mouthful, so I'll explain this first. What I'm showing you is the return period in the future climate of a storm that had a 1 in 100 year return period in pre-industrial conditions, so before we warmed the planet. And where you see red is where the return period of a 1 in 100 year storm is increasing, so the return period decreases, it becomes more frequent. And where it's blue means the return period is increasing, or the frequency of the 1 in 100 year storm is decreasing. So basically blue is where the hazard is increasing, and blue is where the hazard is decreasing, and red is where the hazard is increasing. So you can read it intuitively. And you can see largely in the Western Pacific, there is a big increase in the tropical cyclone with a 1 in 100 year storm frequency. And in the Atlantic, it's somewhat of a mixed signal. You see a big increase in the southern Atlantic, but more of a mixed response in the Gulf Coast. But it's likely that tropical cyclone hazard will increase everywhere. And I have another asterisk here, subject to regional variations. And this is actually a large source of uncertainty. That's a huge topic of open research right now. And it largely has to do with how the world warms. As I showed you many slides ago, I pointed out the potential intensity is increasing a lot in some places and not a lot in other places. That is related to this problem. We have an idea of what the average temperature might look like of the ocean temperature change in the future, but we don't have an idea how the pattern of that ocean temperature might be, meaning that it can warm more in some places and warm less in other places. And that turns out has a big effect on tropical cyclone hazard projections. So this is a big source of uncertainty. So unfortunately, I don't have an answer for you, but this is what the state of the art is right now. So more broadly speaking, in response to anthropogenic emissions, tropical cyclone hazard is expected to increase. Wind hazard isn't the only hazard. But we do expect higher intensities and also lifetime maximum intensity. So lifetime maximum intensity is very simply the strongest intensity over the entire lifetime of a storm. So it's peak intensity. We also expect increased total precipitation and rainfall rate. So events like Helene might become more common. And this is largely a result of the increased temperature of the atmosphere. Also worsened storm surge because storms are getting stronger. And this is coupled with sea level rise, which compounds the effect of coastal flooding. And tropical cyclones are generally expected to get worse. And all of these are largely due to an increase in the potential intensity, as we looked at earlier. And it's also a result of the increase in the temperature of the ocean and atmosphere. So these are kind of where our field is at in terms of understanding tropical cyclones. There's a lot of things we don't understand. For instance, how will the frequency of tropical cyclones change? So right now, there's around 90 tropical cyclones that occur every year, annually. And we actually don't know why there are 90, which is basically a big roadblock into understanding how that number will change with climate change. And it's a very tough problem that I won't get into today, but frequency is a big uncertainty for tropical cyclone activity in the future. Okay, so it changes the hurricane damage. If the hurricanes get stronger, there will be larger hurricane damage if all else stays the same. Turns out we're actually building more properties. People are moving towards the coast, so that, I mean, who doesn't want to live by the ocean? But that's actually leading to larger exposure on the coast. But in any case, changes to the hurricane damage will have large societal ramifications beyond the loss of life and community displacement. So I don't want to say that these things are not important. Actually, these loss of life and community displacement are the most important parts to me. However, forecasting has gotten so good now that the amount of lives lost to hurricanes is actually a very, very small compared to what it was 30 years ago. So we'll talk about money now because that's how money talks. That's how you get people to talk. So reinsurance is insurance. And before we talk about money, I want to just talk about a little bit about insurance and how people bounce back from hurricane events. So reinsurance is insurance that insurance companies purchase from larger insurance companies. That's where the reinsurance comes from. And that's to pass on highly correlated risk. So let's say you're a home insurance company in Florida, and a hurricane could come by and totally wipe out all of the homes that you insure and billions of dollars of damage. You have no way to pay out that capital. What you do is you buy reinsurance, and that basically passes on some of the risk to a company which insures lots and lots beyond just the state of Florida, and that allows you to diversify your risk and also build more capital to pay out losses. And hurricanes cost billions of dollars in highly localized regions. We saw in the figure before, hurricanes are pretty small in area, 50 kilometers. So if you're in a local insurance company, there's no way you could sustain if a hurricane came and destroyed all of the homes that you insure. And this is a big field in it has been a field before, but I think it's rising in popularity, catastrophe modeling. And it's basically how we can model reinsurance firms need to price, the reinsurance market needs to price the cost of reinsurance so that they can pay out in the event of losses, and also they want to take some money on. And that is all a very delicate process that occurs, and it needs catastrophe modeling, which models how often these hurricanes happen and what is the cost of them when they do happen. So the big picture is that reinsurance exists to protect all of us from catastrophic events. So when you buy a home in the future, some of you, it might be possible for you to do that in 10 years, but when you buy a home, you want to buy insurance, and that insurance you're buying from an insurance company, and that insurance company most definitely is going to purchase reinsurance from somewhere else. So this is from the New York Times, average home insurance premiums. So a lot of this data is kind of murky because insurance is private, so you have to get the data from insurance companies or ask people. And basically it's color coded by average home insurance premium. So the higher it is, the more insurance costs. I think that the dots are where they have limited data, so you should trust the data in the stipples less. But you can basically see where there's a lot of weather-related events. This is tornado events happen a lot in the Midwest. There's hurricanes in Florida and along the coast in the Atlantic, and there's also wildfires in Colorado and California. So those are the three of the major costs for weather-related hazards in the US. Of course, this is all, your risk is not always going to correlate with how much you pay in home insurance because there's state regulations and there's a lot of policy involved. So you can also get involved in this problem by doing policy. But this is just what the average home insurance premium is from this data in 2023. So what I'm showing here is now the hurricane reinsurance cost. This is the average premium. I misspoke. This is the average premium over the course of time, over the past 10 years, based on a risk quintile. So basically, the higher your quintile is, the more weather-related risk you have. So you can imagine if you're in this red dot, you're in an area that experiences more tornadoes or more hurricanes, more severe thunderstorms, hail, or wildfires. And here is where you have less of that. So you can imagine Ithaca would be somewhere down here. And you can see for this highest quintile over the past 10 years, the average premiums have really increased a lot. So this represents an insignificant or a non-negligible burden to homeowners. And so the average premiums have risen substantially in risk-prone areas over the past 5 years. Now this is the thing that I was mentioning earlier. This is the reinsurance cost. So this is the Guy Carpenter, which is a reinsurance broker. This is their reinsurance price index, which is basically some non-dimensional index that tells you how expensive reinsurance is. So purchasing reinsurance. Now you're an insurance company that wants to buy reinsurance. And you can see over the past 5 years, it's almost doubled. The reinsurance costs have almost doubled for insurance companies. So at the same time of these annual premiums increasing, insurance prices have increased by somewhere around 85%. So it's a big increase. So one of the things that you can state from this is that reinsurance prices are being passed through to home insurance premiums. So the reinsurance market is increasing because these insurance companies that buy reinsurance, then they're passing on that cost to the consumer, to the person who needs to insure their home. But why have reinsurance prices increased? Actually, we don't really know. It's only happened over the past 5 years. Is it due to climate change? Can climate change manifest itself in 5 years? Or is it just financial black magic? They just increase the cost because they expect increases, but there's not really, it's not due to climate change. So it's an open question. And this basically is a broader open question, is how will tropical cyclone risk evolve in the future? So we don't really have a good idea of this, and the reason is, it's a really challenging problem, not only because of the uncertainty with which the climate will change, and so I had a lot of asterisks on the slide a few slides ago. There's actually a lot of uncertainty in that, because we're really trying to go from a large-scale climate change to local changes in extreme events. So 1 in 100-year events or 1 in 200-year events. It's just really, really hard to go from large-scale climate to local hazard. And that is basically one of the, or that's what this low signal to noise ratio means, is that when you try to hone in on what climate change is going to do on a very specific municipality or local region, it's very hard to do that. You need models that can have large sample sizes and have robust metrics to compare with observations, and even then you have to deal with the uncertainty with how the world will warm. So that's a big uncertainty as well. Okay, so thanks. You can get in touch if you want to talk to me. This is a little advertisement for our department, Earth and Atmospheric Sciences. Anything of this interests you, you should feel free to talk to me. I promise I don't bite. What I want to end on is that there's really a large array of problems to work on in climate change. One aspect of it is the things I talked about, which is hazard, but as I alluded to earlier, you can work on climate finance or climate policy. These are all growing areas that need bright young minds to work on. So we can solve these problems in many different ways, and it really requires interdisciplinary science. Okay, great. Thanks for your attention.
Do you want to call on people? Or should I
You go ahead. Go ahead.
With the intensity of tropical cyclones increasing due to climate change, how can we minimize the impact of the storms?
How can we minimize the impact of the storms? Well, there's many different ways that people will try to adapt. One, we can stop incentivizing people to move to the coast and build expensive properties on the coast. But two, a lot of people are thinking about building seawalls or natural adaptation mechanisms. So people are, for example, one of the things that's been proposed is to build a seawall to protect New York City, for example. So those are things that people can try. But a lot of adaptation is expensive. It's very expensive. Or having better building codes, for example, right? So adaptation is very expensive, so people have to do thorough cost analysis, benefit analyses to whether or not it's worth doing adaptation. But there are lots of different things being proposed. Mitigation is also one of them, like injecting aerosols into the stratosphere to reduce the amount of warming that we get.
So basically with the climate models, that's also, this is really interesting. What's the biggest issue when you're making climate models? Obviously, not all climate models are perfect. Besides the unpredictability of tropical cyclones, what is the most difficult part about making these models?
The most difficult part about making a climate model or making a climate model prediction with respect to tropical cyclones?
With respect to tropical cyclones.
Yeah, well, climate models just have a really, really hard time representing tropical cyclones. So they do a decent job of representing weak tropical cyclones, but not the strongest ones. And so that basically makes them kind of useless because we don't care about the weak ones. We care about the strong ones that cause the most damage. And we want to make predictions about those. So that is one of the challenges that we have. I shouldn't say we don't care about the weak ones. They do cause damage, but the strongest ones are really what we try to plan for. When engineers make building codes, they want to know what the 1 in 100 year storm is, right? So that's how they make their building codes.
Hi. Do you think that current insurance and reinsurance companies fairly compensate victims of natural disasters? And if not, what can they do to make it more equitable for everyone?
Yeah, that's a great question. Way outside my field of expertise. I'm not an economist. I will say that there are a variety. There are a variety of things that people can do to purchase insurance. For example, like wind insurance and flood insurance are different. So your home is not going to be totally covered whether or not you buy one or the other. The other thing is that insurance companies or reinsurance companies typically sell parametric insurance, which is different from your traditional insurance. Traditional insurance, right? You buy, you tell people what your home is valued at, and they cover you. And then when your home gets damaged, you file a claim, and you say, okay, these are the things that got damaged. This is the money that the home was worth. Can you pay me this? And so that process takes months to not years to occur. Parametric insurance is a little bit different in that there's an agreed upon payout based on whether or not a storm happened. It's called a trigger. And that basically, if that trigger happens, then you get a certain payout. There's no claims process, no filing process. It's all really quick. It happens within a span of weeks. And so that basically can help with the payout speed of when there's a loss event. But as opposed to fair or not fair, I couldn't give you an answer to that outside of what I do.
So thank you so much for the presentation, Professor Lin. It was really fascinating to hear all about tropical cyclones. Going back to the more physical side of the explanation, you said that the potential intensity could increase in the future because of a greater disequilibrium between the ocean heat and the atmospheric heat. And I wonder why that is, because we're always talking about how humans are putting CO2 into the atmosphere, which heats up the atmosphere first, which goes on, and then the ocean goes on to absorb that heat. Shouldn't that disequilibrium be smaller rather than larger?
CO2 is a greenhouse gas that has a forcing both on the surface and the atmosphere. So it warms both the ocean and the atmosphere. The big difference is the latent heat. The ocean is at a warmer temperature than the atmosphere. And basically, the amount of latent heat you have scales exponentially with your temperature. So the ocean just has more latent heat than the atmosphere. So when you warm both, because you have the ocean, just latent heat exponentially increases more than atmospheric latent heat, which is at a smaller temperature, then that difference increases, even if they have the same temperature difference, which they don't. But it's a little bit complicated. We can talk after if you want.
Hi, Professor Lin. Thank you so much. You mentioned about the lack of it requires a lot of data to simulate a good model of 1 out of 1,000 chance. I wonder if there's a conflict between those models that are focused on the high category that could create more impact than, but they also happen less frequently and has less data to train, and how are some solutions we could conquer that? Thank you.
Yeah, that's a great question. I mean, a lot of what we do has to be benchmarked on the observational data, and as you say, the observational data for a lot of things is just not very good, especially for rare events. So, my answer is that we try to benchmark what we do based on theory. So you know, it's definitely going to be a trade-off between like having a model that can simulate a lot of events, but not knowing what the tail distribution has to be. There's going to be things that we parameterize or tuning variables we tune to match with observations, but we also know the observations aren't perfect. So when we compare to observations, we put error bars on everything to make sure that that things are consistent. So one thing, I think it turned out, one thing that I do is if you have a large data set, let's say you have 1 million synthetic hurricanes, but your observational data set is only, let's say 500, you can bootstrap or subsample your synthetic data set to the same size as your observational data set and just look at the spread and see if that spread covers your observational data set. And that's one way with which we can account for uncertainty in the observational data set. But the uncertainty is very large. And that's something that, actually, if you talk to like an insurance company and you show them this CAT model, right? They want the CAT model to look exactly like the observations because that's what happened in the past. And it's very hard to convince them that, look, this error bar is actually pretty big when you look at it. And I didn't show it in these slides, but the error bar for the estimates of the hazard return period curves are actually pretty big when you take into account that we only have 40 years of history. So to answer your question, we do our best. We try to take into account the uncertainty, but there's just certain uncertainty that we just cannot get rid of.
Yeah, thank you so much for your talk. You mentioned that it was like difficult for you to convince like government and people to take like preventative action against hurricanes. I was wondering if you can talk more.
Mention that?
Oh wait, like you talked about how like there's a need for like activism or like
Actionable science.
Actual science, sorry. Yeah.
That means that we want to produce science that people can use.
Yeah, so how do you like communicate that to governments and people in a way that would like encourage them to take preventative action, or like is there a certain threshold for like risk that you have to prove to governments to actually like want to adopt solutions?
Yeah. I myself do not work with government. I work with reinsurance and insurance companies. One of the things that is hard for me is when I talk to an everyday consumers, right? If I show them a return period curve, they're going to be like, what is this? Why do I even care about? Why do I care about that 1 in 100-year storm, right? I'm not even going to be living in 100 years. That's how they interpret risk. But that's not really what it's meant, right? Humans are known to have a very poor judgment of risk. Like that's why we are so scared of flying, but we don't mind driving at all, even though flying is safer than driving. So one of the things that we're trying to do, working with this reinsurance company, is put those return period curves and all of that into a single number for people to use. So we have a project, for example, that's I'm working with social scientists that are trying to package all that uncertainty and that risk, different return period curves and uncertainty around that into basically saying, how can we package this information in a way that people can digest and act on, right? Should I buy a home in this particular area? That's the things that people are thinking about, right? Not what is the return period curve. So there's definitely people are working on that. Climate change and communication is a key part of what we try to do.
Thank you.
Hi, I had just a question about how you measure the thermodynamic state of the ocean or the atmosphere in like the proportionality equation.
Measure the thermodynamic disequilibrium
Yeah.
of the ocean and atmosphere?
Well, yeah, for the ocean or the atmosphere.
Well, you just simply need the temperature of the ocean and then temperature of the atmosphere and the relative humidity of the atmosphere. So these are all quantities that you can get by, if you fly into a hurricane and you drop a little, we call them drop sondes that basically float down and they get swirled around, but they measure all of these things, then you can measure that. But we can also do it in numerical models by just taking what the model simulates.
Hi, thank you for speaking with us. I was wondering, how much does your research and like particularly the downsizing or downscaling, sorry, how does that overlap with research on other like major events like tornadoes and heat waves and everything, since those are all also sort of being looked at when it comes to climate change?
Yeah, that's a great question. So my method basically only applies to tropical cyclones because we're using kind of highly idealized physical equations that apply to hurricanes. Tornadoes apply in a very different regime of the atmosphere. They're much smaller. And frankly, we know much less about tornadoes than we do hurricanes. But there's no reason why someone can't do it, right? If there are different people working on this problem with different approaches, different downscaling methods for all kinds of extremes. There's a lot of other extremes like squall lines, thunderstorms, hail, right? Snow on rain events. These are all things that we have to apply our different various methods to do because they are not being properly simulated by climate models. So it's a big area of active research that is totally open to do.
For some of the remedies that you answered, like the question up there about like the seawalls and everything, where does like that money come from, and like are the locals like impacted by that, and like how do they feel about some of these remedies happening?
Yeah, I'm not sure. So that was a scientific paper that I was thinking about. I'm not sure who paid for that scientific study and who in the end would pay. A lot of it probably, I assume a lot of that is going to be on the government. One of the interesting things about climate change and climate justice more broadly, for those of you thinking about this problem, is that a lot of the damages for climate change are disproportionately produced from, or a result of the emissions from a lot of Western countries and countries, or basically there's a huge disproportionality in the amount of emissions that the United States or Europe or China, for example, does compared to other countries. But in the end, it's the countries that cannot adapt, that pay the biggest. And so there's been a push, for instance, in the World Bank to have what we call loss and damage funds. And so essentially, let's say a hurricane comes and hits the Philippines, which has not been a historical big emitter of carbon dioxide. And we find out that climate change made this event 10% worse. Then this loss and damage fund would go and say, okay, the total cost of this event was $1 billion. We will pay you $100 million to help. So that is one avenue. And the people who contribute to this loss and damage fund are going to be the United States and Europe, for example. But obviously, the US contributed, like, I think on the order of $5 million, something puny, right? It's going to be up to policy and international policy, I should say, to help. And tropical cyclones are, of course, not the only aspect at which the world suffers from, right? There's a lot of other hazards and weather events that droughts, for example, that other countries will have to deal with, even though the US, I say we, the US, have been a majority of the emitter in the past. Yeah.
So I think we should end it there. We're almost at time. So let's thank Jonathan again.